Hello and welcome to this short tour through our virtual PSSP labs, or rather through our K-project PSSP. PSSP means Photonic Sensing for Smarter Processes. Our aim is to develop tools based on photonic sensing technologies to enable our company partners to realize smarter processes. My name is Regina Elmecker and I will guide you through this tour. But let me first introduce you to some relevant people in the project. Scientific Manager and Head of Scientific Partner Recent, Peter Burgholzer. Key Researcher and Head of Scientific Partner UAS, Hans Kastner. Key Researcher and Head of Scientific Partner IAP, Johannes Pedanik. Key Researcher and Head of Scientific Partner IME, Bernhard Jacobi. Project Manager R&D at company partner Lenzing AG and Chairman of the PSSP board, Thomas Röder, and the organizational consortium leader from Recent, Robert Holzer. The PSSP consortium is managed by Recent, an RTO located in Linz. Recent is the research center for non-destructive testing and is specialized in the development of photonic sensing technologies. There are three more scientific partners in the consortium: the University of Applied Sciences in Wels and two institutes of the Johannes Kepler University, the Institute of Applied Physics and the Institute for Microelectronics and Microsensors. And these are our 12 company partners: the brewing company Braunion Österreich, the polymer producer Borealis, sensor specialist E+E Electronics, producer of wood-based cellulose fibers Lenzing AG, Upper Austria, who is producing industrial resins, Nemag Linz, producing aluminium parts for the automotive industry, Plaza & Teurer, specialist in service trains for railway tracks, the salt producer Salinen Austria, the steel producer Voestalpine Stahl Linz, and Voestalpine Stahl Donawitz, who is producing steel, for example, for rails. Two companies are not located in Austria. These are Linzers Messgerät in Germany, who is producing equipment for thermodynamic experiments, and Qorvo in Florida, USA, who is developing semiconductor elements for mobile phones. Before starting the lab tour, we would like to point out that this short video can only give you some impressions. For more technological details, just get in touch with us. We want to show you things which not only are great, but also look good. So let's start with the tour. We will take you to the labs of our 4 scientific partners and show you a bit of our equipment and work. Some highlights, selected results and special publications. Let's start with some topics at Recent. First, we take you to the laser ultrasound labs, where the colleagues are working on the physical characterization of metals and semiconductors for various companies. Christian Kerschbaumeier and Martin Rizzi will tell you more.
Laser ultrasound is a contactless, non-destructive testing method, where a broadband ultrasound wave in a sample is generated by laser pulses and detected by laser interferometry. A great advantage of laser ultrasound is the possibility to measure on hot or glowing surfaces. In the PSSP project, we are working with a highly specialized tool, developed together with the company Linzeyes. We upgraded a dilatometer, a thermomechanical test bench, to enable in situ laser ultrasound measurement. Thus, we can obtain metallurgically important information such as phase transformation, elastic constant, grain size and Poisson ratio of a material. 3 physical quantities are used for these evaluations: the longitudinal speed of sound, the frequency-dependent ultrasound attenuation, and ultrasound resonances in sheet metals. This project has enabled further cooperation with the Czech company COMET and with the German University of Saarland, as well as an Austrian bridge project together with the Montanuniversität Leoben.
Hello, my name is Martin and I will show you another application of laser ultrasound. We are not investigating bulky metal samples here, but rather delicate micrometer scale structures from our company partner Qorvo. Qorvo is a company in the United States which is producing electroacoustic filters for telecommunication devices, like mobile phones or routers, which operate at low gigahertz frequencies. Our goal is to characterize the filters and also the raw materials they are composed of, like metals and piezoelectrics. And we are doing that by measuring acoustic plate resonances in the gigahertz regime with our frequency domain laser ultrasound setup here. The obtained results from these measurements, like the acoustic material attenuation for example, will finally help Qorvo to design and optimize their filter devices, and I'm confident that in the near future many mobile phones will be equipped with recent technology.
Next up is Robert Zimmerleiter from Recent's Infrared and Raman Spectroscopy Group, presenting work in the field of chemical characterization.
Here at the Infrared and Raman Spectroscopy Group at Recent, we use modern MEMS-based spectrometer technology which has the potential to revolutionize infrared spectrometer instrumentation. Compared to conventional spectrometers, these devices are extremely compact, lightweight, have a low power consumption and are much more cost efficient. In the PSSP project, we use such devices for example for inline moisture measurement, where we exploit the strong absorption of water in the near-infrared region of the electromagnetic spectrum to precisely measure product moisture. This application is already successfully demonstrated in the production line at Lenzing AG. We have also issued a success story on that topic. Furthermore, inline monitoring of formaldehyde concentration, measurement of quality parameters of spin dope, and the quality control of mold are realized using this novel technology. Together with our newest company partner, Austrian Austria AG, we also investigate state-of-the-art spectroscopy technologies for inline measurements in process fluids during the production process of salt. Here we exploit all measurement signals and data we can get for various substances which are of interest to achieve the highest quality and optimum process control. Currently, we are working towards inline tests using this measurement technology at the salt production plant of Austrian Austria AG.
Now you will see new developments in the field of Terahertz technology, presented by Peter Fossodeder from Recent.
Hello, my name is Peter and we are now here in the Terahertz lab at Recent. The term Terahertz radiation commonly refers to a part of the electromagnetic spectrum between 100 GHz and 10 Terahertz. Several interesting materials such as different kinds of plastics, ceramics, some glasses and even semiconductors are highly transparent for Terahertz radiation, making it an ideal candidate for non-destructive testing. Here, for example, we are reflection scanning a glass fiber reinforced material for hidden defects underneath the surface. The high frequency of terahertz radiation allows us to detect very small defects down to 100 micrometers in size. Another novel NDT procedure that is our key topic in PSSP is terahertz computed tomography. Here, the cross-section of a sample is reconstructed from multiple terahertz measurements under different projection angles. We believe that this novel area of research can have widespread industrial applications from manufacturing of plastic components to medical prostheses.
Before moving to another site, two of our project managers will share their favorite publications with you, Edgar Scherleitner for MP2 and Christian Rankel for SP1.
In MP2, our research aims to support the development of Qorvo's high-tech production process of filters for the mobile communication, as you know from the lab tours. On this topic, we have already published in Applied Physics letters with the title Measurement of the Attenuation of Elastic Waves at Gigahertz Frequencies using Resonant Thickness Modes. It gives a thorough insight how we adapted existing theory, validated it with simulations, and then applied it successfully to real samples and experiments.
In SP1, we deal with measurements from limited information. As a highlight of our work, I'd like to present you this paper published in Analytical and Bioanalytical Chemistry. We developed a novel inline monitoring solution for bioprocesses, which are based on cost-effective microspectrometers. Even though they have a limited range, we were able to get similar information like with conventional FDR spectrometers. And the best thing of our solution actually is that we can measure through the glass wall and make sure that there is no contamination getting into the bioprocess.
Now let's move on to another scientific partner, still here on the campus of JKU, to the labs of the Institute of Applied Physics. Nikos and Stefan will share some impressions and highlights of their work in MP3, which is, for example, applied at Föstalpine Stahl.
Hello and welcome to the Applied Physics Institute. We want to show you our LIBS laboratory today. Laser-induced background spectroscopy, or LIBS, is a rapid chemical analysis method that takes into advantage the use of a short laser pulse, which creates a plasma that contains all information needed regarding spectroscopic elemental analysis. After several plasma events at different sample locations, signal intensity distribution images can be created. The aim of this work concentrates on the use of femtosecond lasers for chemical imaging. Femtosecond lasers produce well-defined craters due to the reduced heat-affected zones, and they're an excellent choice for high-resolution LIBS, which in our case is approaching 1 micrometer and masses in the femtogram range. In an effort to maximally exploit the optical energy of each laser pulse for generating an intense plasma, we are investigating the amplifying role of double pulse LIBS, which includes the separation of the initial beam into two with orthogonal geometry in order to take into advantage the reheating of the plasma from the second pulse.
In cooperation with our company partner voestalpine Steel, we are testing a new method which we call laser ablation spark discharge optical emission spectroscopy. It combines the commercially used electric spark discharge for plasma formation with a nanosecond laser pulse. The exact analysis of the chemical composition of the steel samples is not only important to ensure the quality, it also guarantees that only the necessary amount of rare earth elements and other ingredients are added, which of course saves money and protects and saves natural resources. The advantage of our combined method is the better localization of the electric discharge and the more homogeneous plasma parameters than in pure LIBS.
We are proud to say that our work has already been appreciated by 2 poster prizes at international conferences, LIBS 2020
and the Conference on Solid-State Analysis.
The third scientific partner, who is also located on the JKU campus, is the Institute for Microelectronics and Microsensors. Stefan Klara will provide information on their highly specialized measurement technologies.
Hello and welcome to the Institute of Microelectronics and Microsensors. We are the ones in the PSSP-project who are not doing photonic sensing, but we are equally important for the success of the PSSP because the consideration of complementary technologies has proven very valuable in many cases and is pushing scientific impact and broadness as well as usability and reliability for the company partners. Our research topics are viscosity measurements and impedance spectroscopy for process monitoring. We developed a resonant flow-through viscosity sensor that is chemically resistant to aggressive process fluids and easy to apply to existing production processes. The sensor is machined entirely out of stainless steel and will soon be tested at our company partner Lenzing AG. At the moment, we are investigating the temperature behavior of the sensor. For their pre-production quality monitoring system, we are testing another resonant viscosity sensor. A quartz tuning fork is used as the sensing element. The excitation and signal processing are done by the FluidFox, a multi-frequency resonance tracking system from Microresonant. The small sensing element promises accurate viscosity and density measurements at high sampling rates. We expect to reduce the measurement time for the actual system from 5 minutes to 20 seconds. For the process monitoring using impedance spectroscopy, we developed a very robust flow-through sensor setup which can be installed directly into the production system. The sensor offers 2 impedance electrodes, each with a guarding electrode. Every minute an impedance spectrum is measured and provided to the process control system.
Now we take a journey of about 20 minutes by car to the city of Wels, where we visit the campus of the University of Applied Sciences, Upper Austria, the Fachhochschule Oberösterreich. The highlights of the research group for computed tomography are presented by their leader Johann Kastner and Sarah Rendl.
Welcome to the CT Group. The CT Group is the research group for X-ray computed tomography at the University of Applied Sciences, Upper Austria in Wels. In 2014 we started our research and we got the first CT device. Today we have 4 different CT devices and 16 employees are working for the CT Group. The CT Group consists of researchers from different disciplines covering material science, physics, mechanics, automation, biology, food processing, software and visual computing. For a technical topic, the proportion of women is remarkably high. There are 6 women in the CT group. We work on industrial projects, national and international research projects. Our main topics are CT for material characterization, development of new CT methods, and development of CT data processing methods.
As Professor Kastner already mentioned, our group owns 4 different computer tomographs. The RayScan 250E is our oldest and biggest CT device. It has 2 different sources: a microfocus X-ray source, which is suitable for high-resolution measurements, and a minifocus source for high penetration lengths. The detector implemented is an amorphous silicon detector type, converting X-rays via a scintillation layer into visible light. A minimum voxel size of 5 micrometers can be achieved. It is suitable for bigger samples with a maximum weight of 80 kilograms, a diameter up to 310 millimeters, and length up to 1.8 meters. On the contrary, we have a GE Phoenix Nantom 180 NF. It is a high-resolution sub-micrometer CT device. For samples up to 68 times 150 millimeters, we can achieve a minimum voxel size of 0.5 micrometers. The third CT device is the Bruker SkyScan 1294, which is equipped with a specially designed microfocus X-ray source, an 11 megapixel X-ray camera, and a precise free-grating Talbot Law X-ray interferometer. The fourth and newest CT device is the RX Solutions EasyTom 160. The system includes a nanofocus X-ray source, which can be mounted with a tungsten or an LRB6 filament. The device can be operated either with a flat panel detector or with a CCD camera for lower energies and higher resolution. With this device, steel plates and steel cylinders from voestalpine were measured and statistical data was acquired concerning non-metallic inclusions in steel. This data formed the basis for the automatic detection of defects in voestalpine steel sheets as described in the core document. Aside from CT devices, the CT groups also offer software solution for computed tomography, for example the simulation software SimCT. With numerical simulations, we worked for the company Nemak, who produce aluminum casted cylinder heads for the automotive industry. We supported during the initial teaching phase of the SAIS automated defect detection software. Additionally, also the scan parameters were optimized with parameter studies using SimCT. With the software and the loading robot, the inspection can be fully automated, generating a throughput of up to 400,000 parts per year with scan times of 40 to 400 seconds.
As you have heard from Sarah, CT simulation can help in many different ways. To find the optimal CT measurement parameters or to investigate the influence of different factors on the results. Another important application of CT simulation is the generation of artificial CT data to test new data processing algorithms or to investigate the detectability of certain defects. We are regularly publishing articles on these topics. Every year the CT group organizes the Conference for Industrial Computed Tomography. The last one was held in February 2020 at Wels with about 300 participants from 31 different countries. The conference is aimed at the interface between research and business, and it's really great that around 50% of the participants are from industry. Following the conference, 12 selected papers were, after a successful peer review process, published in a special issue of the journal Non-Destructive Testing and Evaluation.
A project like PSSP has always the challenge to serve at least 2 different interests at once. On the one hand, we want to strive for highest scientific excellence. On the other hand, we want to support the needs of our company partners in the best possible way. These 2 dimensions of impact achieved are sometimes conflicting. But in fact, we believe that we have done a good job in balancing those needs for both sides so far. We are proud that the PSSP board, the supervisory committee, is headed by an experienced industrial researcher. Thomas Röder from Lenzing AG. Thanks for your statement on your impressions of PSSP.
PSSP is our possibility to realize long-term research projects on issues that we could never solve with our know-how alone and for which there are no ready-made solutions on the market. For example, our newly developed bobbin moisture detection based on near-infrared spectroscopy. Thanks to our PSSP cooperation, we can use a brand new NIR microspectrometer to measure the moisture of filament bobbins for our newest fiber development Tensor Lux. This spectrometer is a cube of about 5 centimeters length and costs only 10% compared to a standard near-infrared spectrometer. We are faster, we save money and space, and improve the quality of our newest product. But let yourself be inspired by our work in PSSP, it is worth doing it.